Hello, everybody. So the goal for this short lecture is to understand groups of symmetries like the ones that we talked about with the freezes in the context of the definition of a group and the other examples that we've looked at. So what do we mean by saying that symmetries form a group? So at this stage, we know that a group is a set of objects with a binary operation. It has to satisfy various properties like having an identity element and having inverses for its elements, and so on. So if we talk about symmetries of a geometric object like this equilateral triangle, what do we mean when we say that they form a group? Well, first question maybe is, what do we mean by a symmetry at all? So most of us would probably agree that an equilateral triangle is sort of a fairly symmetric kind of thing. And certainly amongst all triangles, it's somehow the most symmetric one. And that an isosceles triangle is somewhat symmetric, and that an irregular triangle is sort of less symmetric than any of those. So what do we mean? Well, by a symmetry of an object like this triangle, we really mean a way of taking it from picking it up as a rigid object, moving it around in space, maybe rotating it or switching it from front to back like that, something like that, and putting it back so that it returns to the position that it already occupied. So of course we can just leave it where it is. That's a symmetry, it's a fairly boring one. We could turn it through a full rotation of 360 degrees. That would be a symmetry of any flat object like this. But what else can we do? What can we do with this triangle that somehow captures the fact that it's an equilateral triangle? Well, we can rotate it through not just 360 degrees, but through 120 degrees. That wouldn't be a symmetry of any object, but it is a symmetry of this equilateral triangle. The convention in this game is that you take symmetry in the anti-clockwise direction to be symmetry sort of in the positive direction. So a rotation through 120 degrees means an anti-clockwise rotation through 120 degrees. So this way. Okay, so that's a symmetry. We could do it again. And of course, if you do one of those and then the other, you've rotated through 240 degrees, which is 2/3 of a full turn. The other thing that we might notice that we can do with a triangle is we can do some reflections. So for example, if we take the line that goes from one vertex to the midpoint of the opposite side, like this vertical line, we can reflect the triangle in that line, and we again put it back in its original location, though not quite exactly in its original position. We can also take the line that goes from this vertex to the midpoint of the side opposite. We can reflect in that line, and once again, we've returned the triangle to its original position. So with this equilateral triangle, we might notice that it has three reflections. There are three medians that join a vertex to the midpoint of the opposite side. All of those are lines of reflection of the triangle. So there are three reflections, and there are also three rotations. There's a rotation through 120 degrees. There's a rotation through 240 degrees that would do 2/3 of a full turn. And there's also the rotation through 0 degrees, which we do consider to be a rotation. It's going to form the identity element of our group, and which is also a symmetry of the triangle. So that's basically the symmetry that just leaves it where it is. So I guess from this sort of picture of a triangle, and I think it's a good idea when you're thinking about this to make your own equilateral triangle and try this out. What are the different ways that you could pick up a triangle and put it down in a different position so that it occupies the same space that it did before? There's the one where you do nothing, just pick it up and put it straight back. There's the rotation through 120. There's the rotation through 240. There are the three reflections in the vertical axis and in the two sort of non-vertical axes. Okay, so a triangle has 6 symmetries, 3 rotations and 3 reflections. And what we're going to talk about in this short lecture, and we'll have a few slides to accompany us, is that these 6 objects, if we think about how to put them together appropriately, form a group, just like the other groups that we've been talking about. Of course, in order to do that, we need to say what the operation in our group is going to be. So we'll have a few slides now, and we'll have a look at that. Okay, so to try to explain that in slightly more formal terms, here's a picture of our equilateral triangle. It's got vertices A, B, and C, and its 3 axes of symmetry are labeled L, the vertical one, and the other 2 are labeled M and N, passing through B and C, respectively. So we're going to try to keep track of what happens when we move this triangle around with various symmetries. So remember the 3 axes that are in the picture here, labeled the 3 reflections, the 3 axes of reflections. There are also the rotations through 0, through 120 degrees, and through 240 degrees, all measured in a counterclockwise direction. And that's just a sort of convention that we agree that if we are talking about a rotation through 120 degrees, we mean a counterclockwise rotation through 120 degrees about the centroid here. So that would take A to where C is, C to where B is, and B to where A is. So that's a picture of our triangle. If we look at the 6 symmetries, we can observe what they do by just sort of keeping track of what they do to all the 3 vertices. So the identity symmetry is the one that just leaves the triangle where it is. You can equally well think of it as a rotation through 360 degrees if you want to. It just means basically pick up the triangle if you want to, but put it back exactly as it was before. So it takes the 3 vertices A, B, and C to their original positions. It doesn't really do anything. The rotation through 120 degrees is supposed to be indicated by this picture. It rotates counterclockwise through 120 degrees. So it takes vertex A to the lower left position where C is. It takes vertex B to where A is, and it takes vertex C to where B is. So this is a picture of what it does to the triangle. So it's a rotation in a counterclockwise direction through 120 degrees, 1/3 of a full turn. The rotation through 240 takes A sort of 2 steps round in a counterclockwise direction. So it takes A to where B is, B to where C is, and C to where A originally was at the top here. So those are the 3 rotations. The 3 reflections, the reflection in the vertical line, which was called L, well, that keeps A where it is, and it swaps B and C. So we can see that reflected here, that indicated here by the labels on the vertices. The reflection in M is the axis that passes through B and the midpoint of the side AC. The reflecting the triangle in M leaves the vertex B where it is, but it swaps the other 2, A and C. And the reflection in N passes through C, so the reflection in N leaves C where it is and swaps the vertices A and B. So there's a few points here. One is just sort of noting what it does, what each of the symmetries does to each of the 3 vertices is a way of sort of keeping track of what all of these symmetries do. And the other remark is that associated to each one of these symmetries of the triangle, we have a permutation of the 3 vertices, a rearrangement of them. So basically, each of the symmetries permutes the 3 vertices, and that's going to be important to us later when we talk about groups of permutations. So I suppose the comment for now is that each symmetry of the equilateral triangle can be considered as a permutation of its vertices. That's going to turn out to be important, not only from the point of view of sort of keeping track of things and knowing what each of the symmetries does, but also actually from the point of view of group theory itself as well. We see a connection between this group of symmetries of the triangle, which is kind of a geometric thing, and the group of permutations of the 3 vertices, A, B, C, those 3 things. And that's more of a combinatorial gadget, but we'll see that they're in some way exactly the same thing. Okay, so that's the picture with our 6 symmetries. Now, okay, what are we doing here? We're supposed to be talking about how the symmetries of a triangle form a group. And we have seen by now in the examples and in section 1.2 that a group is something where you have elements. They have to have a binary operation on them. And that binary operation has to satisfy various properties. It has to be associative, and we have to have an identity element, and we have to have inverses for each element that we have. So, okay, so in what way is the set of symmetries of a triangle then a group? Well, the key point to note, first of all, is that the elements of this group are the actual symmetries. And this can be a tricky thing to kind of deal with because, we're used to situations maybe where the elements of a group are numbers or matrices or functions of some kind maybe, but in any case, some kind of sort of fairly concrete things, like an integer or a complex number. So here, the elements of our group are actually symmetries. So the elements of this group are things like reflecting the triangle in the line L, or rotating the triangle through 240 degrees, okay? The triangle itself is not an element of the group. The vertices of the triangle are not elements of the group. The elements of the group are these actual symmetries. Okay, the binary operation on the group is the act of taking 2 of these symmetries and performing one first and then the other one. Okay, so it's a composition operation. So basically, the symmetries of the triangle, we agree, are all possible ways of picking up the triangle and putting it back so that it occupies the same space that it did before without cutting it or tearing it or anything like that. It's the sort of rigid motions of the triangle that are symmetries. So there are 6 of them. But that means that if I pick up the triangle and rotate it through 120 degrees, and then do a reflection in the line L, for example, what I've done overall still puts the triangle back where it started. So it should be a symmetry. So it should be somewhere in this list. And by inspection, I should be able to figure out which one it is. And that's the content of the next slide. So, okay, bit of lingo. D6, this capital D subscript 6, is the name that we give to this group of symmetries of the equilateral triangle. The 6 refers to the fact that there are 6 elements in the group, 6 symmetries, 3 rotations and 3 reflections. Remember, the identity constant rotation. And the D stands for dihedral. So the dihedral groups are groups of symmetries of a regular polygons. Okay, so the elements in the group D6 of symmetries of the triangle are the identity element, which does nothing, it leaves the triangle where it is, the rotation through 120 degrees, counterclockwise, the rotation through 240 degrees, and the reflections in the lines L, M, and N, respectively. And they're written as T, L, TM, TN, because the R is already taken for rotation, so we can't use it for reflection. Okay, the group operation is composition, which we denote by the symbol, little circle, like you use for the composition of functions. And if we, for example, want to take rotation through 120 composed with TL, well, first of all, the way to read this, at least the way that I read it, is rotation through 120 after TL, meaning that we apply the reflection in L first and then apply the rotation through 120 to the result of that. And look at what we've done overall. Okay. Bear in mind as well, when you're thinking about these kinds of examples, there are three lines of reflections, L, M, and N. They're sort of fixed in space. So they don't move when the triangle moves. They're not part of the triangle. They're sort of in the background, labeling the axes of symmetry. Okay. So if you want to figure out, if we do TL first, reflect in L, and then we do rotation through 120, then certainly overall we've returned the triangle to its original location. So what we've done should be a symmetry. It should be in our list. So we can figure out which one it is by just kind of thinking about doing these two operations and looking at what we end up with and looking at the permutation of the vertices that we end up with and comparing it to our list on the previous slide. So here's the triangle in its kind of original sort of home position. There's the line L. So we're doing rotation through 120 after TL. So do TL first. That leaves the vertex A where it is, and it swaps the vertices B and C. Okay, so that's after the step of doing TL, that's where we are. We then apply a rotation through 120 to that. That cycles every vertex one step around in the counterclockwise direction. So it takes A around to the lower left, it takes B over to the lower right, and it takes C up to the upper position. So this is what we end up with. And now we can ask ourselves, okay, well, here's a configuration that we end up with, A, B, C, in that arrangement. This is the configuration that we started with. So overall, if you sort of leave out the middle step, what would you have to do to get from here over to here? What single symmetry would you have to apply? And we can observe that comparing the first picture here to the last one, the vertex B is in the same position that it was originally. The vertices A and C have swapped. So it's a symmetry that leaves B alone, swaps A and C. Well, that's the reflection in the line that passed through B, which was the one that was called M. So we can say rotation through 120 applied after reflection in L is the symmetry TM. Okay, and by, in principle, we can do this calculation for all pairs of symmetries in our setup, D6. We can calculate all these compositions, and we can fill out the table, the table of the entire composition table for D6. So here's the picture. This is the group table for D6. We saw a similar thing last week for the group of fourth roots of unity and the complex numbers. The 6 elements are the identity, which does nothing, the rotation through 120, the rotation through 240, and the 3 reflections in L, M, and N. So here they are labeling both the columns and the rows. And then what we have in each sort of interior position in the table is what we get by composing the element that labels the row with the element that labels the column. So the TN that appears here is rotation through 240 after TL. That's the operation that we get by applying reflection in L first and then rotation through 240. So something that you can do just using the technique on the last slide, and it's described also in the lecture notes, is just calculate this table for yourself, figure it out. The fact that the operation is associative kind of follows just from the fact that it's a composition of symmetries. So if you want to apply symmetry A after symmetry B after symmetry C, you're just applying them in that reverse order: C first, then B, then A. It doesn't matter whether you think of it as A after B after C or as A after B after C. You're doing the same operations in the same sequence either way. The identity element, of course, is the identity symmetry, which just leaves everything alone, doesn't touch anything. And certainly if you compose that with anything else, you're just doing the other thing. And the inverses, well, we can observe by looking at where the identities appear here in the table. Rotation through 120, rotation through 240, those are inverses of each other. If you rotate the triangle through 120 degrees, what you need to do to get it back to its original position is rotation through 240. So the composition of those two things is the identity. Each of the 3 reflections is its own inverse. If you reflect in the line L, what you need to do to get back to where you started is reflect in the line L again. So that's kind of evident here from the fact that when we compose any of the reflections with itself, we get these 3 identity elements along the main diagonal. So that's the dihedral group, D6, the group of symmetries of the equilateral triangle. Something that you can do, and I really encourage you to do it, is do the same exercise for the square, the pentagon. In general, the group of symmetries of the regular polygon with n sides is denoted by d subscript 2n and called the dihedral group of order 2n. So 2n is the number of elements, and in general, for a finite group, the order of the group is the number of elements in it. The triangle has 3 rotations, including the identity, and it has 3 reflections. The square has 4 rotations through 0, the identity, 90 degrees, 180, 270, and it has 4 reflections. It has 2 reflections in the lines that run through the midpoints of opposite pairs of sides, and it has 2 reflections in the 2 diagonals as well. So in general, the regular polygon with n sides has n reflections and n rotations, and those 2n elements form its group of symmetries, which is the dihedral group of order 2n. So the dihedral groups are an important kind of family class of finite groups. They're quite interesting, and people certainly like studying them. One observation that we can make here, just for D6, which is really the smallest of the dihedral groups, since the triangle is really the first sort of example of a regular polygon that we can do this for. We can observe that the group D6 is not abelian. If you're composing a pair of symmetries, it does matter in what order you do it. So for example, if we do TL after rotation through 120, we get the TN here in the table. If we compose the same pair of elements in the opposite order, rotations through 120 after TL, we get a different element, we get TN. And the fact that the group is not commutative or not abelian is visible in the table here. If it was abelian, it would be true that if you sort of reflected the whole table in the main diagonal, it would land exactly on top of itself. So, the TL, well, the TM here, for example, in the 2-4 position of the table would have to match the entry here, which is the composition of the same 2 elements, but in the other order. Okay, so that's D6, the dihedral group of order 6. We're going to meet it a few more times as we proceed, and we'll also meet its friend, D8, the dihedral group of symmetries of the square. So a nice thing that you could do now, if you're thinking about this, would be to think about the version of this story for the square and have a go at writing out the table for that one. Okay, coming up next is our challenge for this week, for this video. Okay, this week's challenge is sort of a physical one. This is a cube, as you can see. And just like we talked about for 2-dimensional objects, such as the equilateral triangle, you can also consider the symmetries of a cube, which is a 3-dimensional object. And like 2-dimensional cases, cubes have both rotational symmetries and reflections. Rotational symmetries about some axis that passes through the center of the cube, maybe, and reflections maybe in some plane. We're not going to worry about the reflections for the purposes of this challenge. We'll just think about the rotations. Your challenge is to describe all of the rotational symmetries of the cube, and they're kind of harder to pin down than the corresponding things for regular polygons in 2-dimensional space. So for example, if you can imagine an axis that passes through the center of a face and through the center of the opposite face as well, so like this, then there are rotational symmetries to 90 degrees, 180 degrees, and 270 degrees about that axis through the center of 2 opposite faces. And of course, there's also the identity rotation, which leaves everything where it is. So those are some examples of rotational symmetries of a cube. The lines of symmetry pass through midpoints of 2 opposite faces. They're not the only ones. They might be the easiest ones to spot, but they're not the only ones. And of course, you can count the number of such axes that you have, and you can count the number of non-identity rotations about each one of them. And that gives you some of the rotational symmetries of the cube. So your challenge is to describe all of them and to give a description in some form that keeps track of them. I'll give you the hint that there are 24 of them in total, including the identity element. So have a look. Best way to do this probably, or the best way to get at it probably, is to use a physical example of a cube, if you have one lying around. And yeah, see how you get on. It's not an easy challenge, I don't think. Good luck with it, and thank you for listening, and we will see you later in the week. Good luck, everyone.